Okay, so the next two chapters we have to go over are chapter 4 and chapter 7. Chapter 4 goes into detail about cell injury. So remember how I said to you guys earlier that disease process begins at a cellular level. So what we're going to do in this chapter is go over all the different injuries and issues that can happen with the cell. The portion of aging and death, we are not going into detail with that. This original PowerPoint was actually way longer. I tailored down some of the information. The information about apoptosis and things like that, I believe you guys have had that information in physiology, so we'll just leave that alone. But I do want to focus on cell injury as far as intracellular things that can occur, as well as cellular adaptations. And we're also going to add in the pictures that you guys picked up in the back. This is where your pictures are going to be part of this chapter. So you may want to pull them out, and I'll tell you which pictures you're going to be looking at when we get to that section. Okay, so for chapter 4, cell injury is actually broken down into two different categories. We have what is called reversible cell injury and irreversible cell injury. So under reversible cell injury, we have something called hydrophic swelling, okay, which is going to be an excess of water that accumulates inside the cell. The cell obviously will get larger, okay, and stretch out. This particular situation, believe it or not, can be reversed. Okay, so if water is excreted, then it can go back to normal. Now you're probably wondering, okay, well, why would water get inside the cell in the first place? Usually because on the cell membrane, there's different ion pumps, okay, that as we know, different channels that allow ions to flow through, freely. So what happens is this: if those ion pumps or channels are not functioning properly, mainly due to a lack of ATP, what can happen is these things can go haywire. You can have ions just going everywhere they want. And if you have a situation where you have sodium influx inside the cell, an influx of sodium inside the cell, what do you think is the next thing to follow? Water. Okay, very good. So this is how water gets inside the cell because of that excess sodium. Now, you're probably wondering, okay, well, why would there be a lack of ATP in the first place? The issue is this: if you remember from physiology, and not to bring back bad memories, however, Krebs cycle, glycolysis, electron transport chain, okay? All of those things, if you remember, are important because we do need to convert that glucose into a form of energy of ATP so our cells can utilize it, okay? So if we do not have enough ATP that's being produced, the cell membranes will not be able to function, which means the cell will not be able to function. Okay, so, oh, I didn't tell you guys this, but your anatomy, yes, will come back to haunt you. Okay, so remember all those slides that you took a look at anatomy, and you wonder why, okay? That was going over normal, okay, histology. What we're going to go over in this course are looking at pathology slides. So as I told you, each week I will give you pictures and images, okay, according to that particular disease. So some weeks you'll have slides or pictures that are just an actual specimen, okay, of a diseased tissue, or some weeks you'll have slides that are just, you know, a histology slide, a pathology slide. And so next week, I would say most of your pictures are actually going to be blood slides, because next week we're actually going to go into leukemias in detail. So we do a whole chapter on leukemias, and then I'll go over some blood disorders and show you some bleeding things that can pop up on the skin. Okay, so looking at this particular one, can you tell me what type of epithelial cell is here? Not squamous, cuboidal, very good. This is cuboidal. Cuboidal, if you remember, excuse me, I used to always tell students, if you look at the nucleus and if you can see that it's nice and round and plump, that's a good sign that it is a cuboidal cell. If the nucleus is a little more squish, that's a squamous, and we know columnar, more stretched out or oblong, okay, shape. Now, to further pick your brain, what tissue type is this? Or what organ? Not the liver, kidney, very good. These are the kidney tubules. A lot of people get that wrong. These are the kidney tubules. And if you remember from histology, the cuboidal cells function in secretion and absorption and things of that nature, which is actually what needs to take place at the kidney level. Okay, so very good. These are kidney tubules. Now, when you take a look on this side, obviously that's the pathology, and as you can see, those cuboidal cells are actually filled up with water, so much to the point that it actually has distorted the tubule. Okay, so you can't even really see the lumen of it. It's just stretched out and distorted. Okay, and believe it or not, that can be reversible. Now, hydrophic swelling, when we think of this, yes, we know water is entering inside the cell, so it's not just only the cytoplasm, but I want you to know that water also enters inside the organelles. So we know that each cell has organelles inside of it, okay, just like, almost like a little human body in itself that has organs. And what happens here, these organelles will also fill up with water and undergo hydrophic swelling, like the mitochondria and ER and things of that nature. Now, going back to the level of organization, if the cell is large, the tissue is larger. If the tissue is larger, the organ's larger. So when the organ becomes larger, the issue here, or I should say the terminology that's used, is what is called megaly. Okay, you guys have heard of this. This is a medical term, megaly, that can be used. Cardiomegaly, I'm sure you've heard of that example. Splenomegaly, hepatomegaly. Okay, so megaly is a term that's used to explain an increase in size and weight of a particular organ. Okay, but just keep in mind that there's obviously some cellular damage that led to that point. Now, intracellular accumulations. So sometimes there can be an excess of things inside the cell that should not be there. So as you remember from anatomy, we know that each organelle has a function. Okay, and so some organelles, like lysosomes, are there to break down materials. And if for some reason, if the lysosomes do not break down the materials that it needs to break down and get rid of it, what happens is this. Now you have an accumulation of waste inside the cell that shouldn't be there. So that is also considered an injury. This accumulation will sit there until it's taken care of. Now, so another accumulation that can occur is something secondary to faulty metabolism. So we know that carbohydrates have to be transported in the cell, as well as other types of particles. Now, they give here an example of the liver as a common site for accumulation. Okay, and we're going to go into this in detail. The liver is a really good example. So, what do you know are some functions of the liver that we know from anatomy, physiology? Functions of the liver. Liver has a lot of functions. One major one.
Doesn't it separate their waste?
Detox. Well, we don't, well, not waste in that sense, but detox. So detoxification. The liver is our main detoxification organ. Okay, I think we should all know that. So go out, happy hour, get too happy. Okay, what happens as you intake, okay, consume large amounts of alcohol, your body will take that alcohol and turn it into a non-toxic substance so it can go flow freely to your bloodstream, through your bloodstream, and you'll be okay. So we have to get rid of those toxins. And not only just alcohol, just keep in mind even drugs, pharmaceutical drugs or street drugs, anything that's a toxin, okay, that's being ingested inside your body will try to convert it to a non-toxic substance. Okay, very good. What else? Some other functions of the liver.
Glucose.
Yes, the liver will actually store glucose in the form of glycogen. Okay, and we know that. That's part of one of our homeostatic type mechanisms that occur when we eat food. So yes, glucose will be stored in the liver when, in the event if we ever need it for gluconeogenesis. Okay, so yes, the liver will store glucose. What else?
Coagulation.
Say that again.
Coagulation.
Very good. A lot of people tend to forget that, and that's extremely important because liver actually helps produce a number of coagulation factors. It helps produce a number of coagulation factors to help clot the blood. Which means if your patient has like a chronic liver disease or some kind of liver issue, is it a possibility they may have a bleeding issue? Yes, because they may not produce enough factors that they need. Another function, bile, very good. The liver produces bile, okay, we know that, and obviously bile has to be excreted at some point as waste product. But what is the purpose of the bile? Very good, to break down fats. Keep in mind that the liver is extremely important in lipid metabolism, okay, it is needed. We need the liver to help break down those fats, okay, because when it secretes the bile, you guys remember from physiology that bile helps break the fat down into little tiny pieces, okay. And one more thing, sometimes people forget this one. The liver is a really good storage for vitamins. And those of you who do eat animal livers, like chicken liver and beef liver, okay, probably know that. It is a very high source of vitamins because the liver stores vitamins there, okay, for the body. So yes. Now, what's the point of going over all of that? Have you ever heard of the condition called fatty liver? Okay, so what happens is this. Let's say, for example, we have a person that's an alcoholic. Okay. And if you have this person that's an alcoholic, what's happening is this. Since the liver is the only really detoxification organ, it's going to focus on detoxifying the body, okay, constantly because this person is constantly drinking. Which means that the other functions of the liver actually take a back burner, like making enough coagulation proteins and things like that. So what will happen sometimes is that it will have a decline in lipid metabolism, which means that now this fat can accumulate in the liver. Okay, so now these individuals will have what is called fatty liver due to the alcoholism. They call that a faulty metabolism. Now, let me show you this picture here. You're not responsible for this picture. I don't have it on your image sheet. However, just want to show you really quickly, and I don't have normal, but this is a histology slide or pathology slide of someone with fatty liver. So what you're looking at here, you see those large circles? Those are considered vacuoles. Sometimes some cells have vacuoles just for temporary storage, okay, for things. But in this situation, these vacuoles are actually filled with fat, okay, because lipid metabolism did not occur. So now the lipids actually just stay there. They actually store themselves within the liver. Okay, so let me go back to this. So, fatty liver, we already discussed. The next one here we have is protein mutation. Okay, so we all know that cells undergo mitosis, okay, for reproduction. And we know that sometimes during mitosis, things can go a little haywire. Okay, so in mitosis, during interphase, we know that we do have different checkpoints, okay, that is supposed to happen, so we can move on, do what we need to do. Now, sometimes there can be an alteration in protein folding, which can now cause an abnormal cell. Even though this is under reversible cell injury, understand that yes, in some cases it can be irreversible, okay, such as like a genetic disorder or even like cancer, okay, because we know cancer is what we call an altered gene expression. So it's just a matter of faulty mitosis. So I just wanted to say that because even though they have it under reversible, it just depends on the situation. The next one here is lack of enzyme. So we know that we need enzymes to break down these substrates to products. And so just to kind of bring it more to like a GI issue, we know that we do need enzymes to break down certain food groups. Okay, so say for example, a person that's truly lactose intolerant, okay, lacks the enzyme lactase. And if they do not have that enzyme to break down lactose, that lactose will actually sit honestly in the GI wall, okay, which is the reasons why they have a lot of cramping and irritation, and it might lead to diarrhea and things like that, because the product is just sitting there just irritating the lining. Same situation they're trying to show you here. If you have just an excess, it'll just sit there in the cell. Okay. Ingestion of indigestible materials. So some things you know that we cannot digest no matter what, and some things we just do not have an enzyme to break down. So let's say, for example, we have a person that is working in an environment with asbestos. Okay, and so they're working with asbestos, and if this person is inhaling this type of material, this type of particle, obviously the body cannot break that down. Okay, and so what will happen is it will get inside the lungs, it'll sit there, and it could start to cause damage. Okay, now again, depending on the amount of accumulation, it can be reversed, okay, via the immune system in that situation, or depending on the amount of damage, it cannot be reversed. Okay, so let me show you another example. You could cross this slide out, go into that. So, this picture here, this image here is a person that has silicone lung. Okay, and as you can see here, my pointer isn't working. Okay, the bluish blackish area, okay, the lung, it has been infiltrated with silica dust. Okay, so this person obviously their work environment may be working around silica, okay, now has inhaled all of this and it's gotten into their lungs. Now, please understand that this situation did not happen overnight. Okay, that amount of damage occurred most likely years of working in that environment. Now, when we take a look at that, I want you to understand that the body will try its best to get rid of it. Okay, so I don't want you to think that it'll just sit there and just let that damage occur. The problem is this: your immune cells will try to attack this. However, when you look at that, we would need like a zillion macrophages to come over to try to eat all of that, okay, which is impossible. Not only that, if you have a zillion macrophages coming over to try to eat that silica tissue, what's going to happen is this. The lung tissue is very thin, as you know, it's squamous epithelium. So do you think that all those macrophages coming over trying to take care of this, is it going to damage the lung tissue? Yes. And so sometimes, as I said to you before, the immune system, when it comes to attack, just because of the severity of disease, sometimes the immune system kind of brings the disease a little more heightened. I don't want to say make it worse, but it heightens the disease, okay? So that's that. Now, even though they have this under-reversible, let's say, for example, if that person just had a little area, okay, and the immune system was able to attack it and get rid of it, that's fine. Obviously, this is something, okay, that is irreversible, okay, which is why we're looking at the specimen. So, that's that. Now, we're going to go over now cellular adaptation. So some of these things, excuse me, we already have heard of in other courses. Now, cellular adaptation, we're going to go over atrophy, hypertrophy, hyperplasia, all that. So you may have heard these terms before. So let's go over atrophy, and we are going to now introduce the pictures that I have on your image sheet. So we're going to add these in now. So atrophy is going to be a decrease in cell size. Okay, decrease in cell size. So if the cell is shrinking, obviously the tissue shrinks, organ shrinks. Okay. So there's a number of things that can cause atrophy, and so we'll go over these. And what I will do is use muscle atrophy as an example. Okay, muscle atrophy is a little easier to use as an example. So disuse could be one cause. And so say, for example, the picture that you guys have on your image sheet is a picture of muscle atrophy, and I would say that that is from disuse. Okay, and so let's say that person may have fractured a limb, had a cast, just kind of laid up for however long, not using the muscle at all, no contraction, nothing's occurring, and so now what's going to happen is there's going to be a subtle atrophy that will set in. God bless you. So you can see the difference. Okay, so that's definitely a good example of muscle atrophy. Yes?
My dad, when he was younger, he had polio.
Yes.
So that's kind of how like his leg looks.
Yes.
So it's just from disuse?
Well,
or
disuse and a possibility of denervation, because sometimes that can attack the nervous system too. So it could have been a combination of both, disuse and nerve supply. So the next one here is denervation. Denervation is nerve supply, or excuse me, a lack of nerve supply. Denervation is a lack of nerve supply. So sometimes in certain disease processes or certain injuries, okay, it may get a person severed a nerve or something like that. If you're not getting enough nerve supply to that tissue or that area, obviously it's going to shrink, okay, because it needs that in order to survive. Ischemia. Ischemia, this is going to be a lack of blood supply. A lack of blood supply. And with ischemia, obviously everything needs blood. Okay, so if you lack the blood supply and getting to a particular area of the body, it is going to shrink, okay, or not survive. Nutrient starvation. I know this one sounds a little strange, but what are we talking about here? So let's say if we're using muscle, again, as our example, if a person is undergoing muscle atrophy, sometimes we know that if you don't have enough nutrients to supply to that muscle cell, it's not going to survive, okay, or it will get smaller. So say, for example, what are the ions that we need for muscle contraction? Calcium, sodium, potassium. Okay, very good. So keep in mind, when we talk about nutrients here, we're talking about ions. Okay, so the ions that are needed for that contraction. Interruption of endocrine signals. As we said earlier, we can't do anything without our nervous and endocrine system. So if our endocrine system, for some reason, the signaling is off in how they communicate with other organs, this can now possibly cause the cells to shrink. And persistent cell injury and aging. So if you keep damaging the cell, particular cell, yes, it will get smaller, as well as we get older, we know what happens. Everything goes south and we shrink. All right, so here are some pictures, and we're going to go over each one of these in detail. Okay, so we went over atrophy, hypertrophy, we're going to go over hyperplasia, metaplasia, dysplasia. So let me just say a little thing about this one. Dysplasia, even though they have this kind of with this category as reversible, I do want you to know that dysplasia is actually irreversible. Dysplasia, when it is actually diagnosed, they do consider this precancerous, okay, or pre-neoplastic. It is something that once the epithelial cells change into a dysplasia, it's not anything you just want to kind of sit and watch and wait and see what's going to happen. It actually has to be removed. Okay, so we treat this, we'll look at this differently. Okay, and I'll get into more detail with that later. So hypertrophy. So hypertrophy, we would imagine, yes, this is an increase in cell size, so the cell gets larger. Understand that there can be a physiological hypertrophy, which would be, let's say, under normal circumstances, and then we can also have a pathophysiological hypertrophy under abnormal circumstances. So let me give you an example of each one. So for physiological hypertrophy, let's say we have, and I'll continue with the muscle example. Let's say we have a guy going to the gym. Okay, he has a membership, LA Fitness, he's going in and he's getting it in, okay, with the weights. And so with his weight training and him working very hard on his weight training, he's constantly causing contractions, okay, of the muscle. And so with his constant contraction of the muscle, he is trying to increase the cell size, okay, because of that constant contraction. Now, not only is he trying to increase the cell size in that manner, he is also feeding his body the proper nutrition, making sure he has adequate amount of protein, staying hydrated, okay, whatever type of supplements he's taking to make sure he bulks up his muscle, okay. That is what we call physiological hypertrophy, okay, because he's giving the proper nutrients to the muscle, proper contractions, and that's okay. If we have, say, pathophysiological hypertrophy, let's say the situation where I have the heart palpitations, okay, and bam, so say if my heart's contracting, okay, and that continues on, let's say, for days, okay, if that goes on like that for too long, what's going to happen to the heart? It's going to get larger, okay, we know the heart is a muscle, so if you continue those contractions, those really intense contractions, the muscle fibers and everything will just get larger. Now that is considered pathophysiological hypertrophy because we wouldn't be in that state if we weren't in elevation with low oxygen. So you have a picture of hypertrophy with the heart, okay, and so this is another one here. It's not the same exact picture, but you can see the difference. So the top portion here, as you can see, is the hypertrophy, okay, and this is the normal. And so this is the left side of the heart, this is the right side of the heart, and as you can see, actually both sides are really large. Okay, you can see how thick that myocardium is. So thick to the point that it's actually kind of closed that little lumen there, which is also probably not a good thing. That would probably cause even more problems. So that's that. Okay. Hyperplasia. This is an increase in cell number due to mitotic division. Okay, so this has nothing to do with size. This is everything to do with the number of cells that's increasing. But obviously, if we have an increase in cell number, obviously the tissue gets larger. Okay, so there's also two ways this develops, physiological and hormonal. So the picture that you have on your image sheet is a picture of a person's heel, okay, so callus formation. Callus formation is actually a very good example of hyperplasia. Okay, so I'll explain. Yes?
Same thing with the hands too?
Yes, same thing with the hands. So let's say this person is maybe, I don't know, a dancer or something's going on, okay, that they're using their feet, okay, a lot. And let's say also the guy that's in the gym all the time, okay, and so now starts to develop callus formation from the weight training. So what you should understand is this. When you have constant friction to the epithelium, what happens is that you're actually increasing mitosis. Okay, so you're, this increases mitosis of epithelial cells. Where you would think it would like kind of strip away, it doesn't do that. It actually increases in the number of cells because that's your body's way of protecting and making a barrier. Okay, so constant irritation or friction, rubbing, causes an increase in mitosis, making that skin thicker. Okay, so that's that area. Now, and that's a good thing, even though we don't want callus formation, but it's just because of what's going on in action. Now, hormonal stimulation is this. BPH, okay, so I think I talked about this before. Benign prostatic hyperplasia. So when men have enlargement of the prostate gland, some doctors believe that, oh, they don't know what it comes from, they think it's idiopathic. But then you do have some doctors that believe it's from a decline in testosterone. So as I told you earlier, sometimes men do have a decline in testosterone as they age. And so they believe that the prostate gland tries to compensate for this by increasing in number of cells. And so the prostate gland gets larger. And it's because of the hormone imbalance.
Sorry.
Yes.
So the hyperplasia with the callus, that's the
Physiological, yes. That's the physiological one. And the hormonal is going to be the example for like BPH. Okay. Metaplasia. This one is different, and I will use smoking as an example. Metaplasia is a replacement of one cell type to another, and I just want to add to this, in the same tissue. Okay, I want to stress that, because I don't want you to think it's two different tissue types. A replacement of one cell type to another cell type in the same tissue or same area. And I'll explain. So I'm going to use smoking as an example, and when individuals smoke, I want you to understand that it will definitely cause an airway irritation. Now, it just depends on the degree of irritation. So whether a person's been smoking 5 days or 15 years, it's still going to be an irritation, okay, each time they take a puff. Now, what is the normal epithelium in the airway that you remember from anatomy? Normal airway epithelium. Pseudostratified, very good. What else? There's another piece to it. Columnar, very good. And there's one more little piece to it. Ciliated. Okay. So let's pull it together. Ciliated, pseudostratified columnar epithelium. Okay, that's the normal respiratory epithelium in our airway. Now, as you know, we need the cilia to sweep out, okay, whatever that may get in there. The pseudostratified, many layered and thickening, okay, is there to help resist abrasions and things like that. So, what happens is this. When a person smokes, let's say we have that chronic smoker, okay, 15 years plus smoking, what happens is this, it will burn off the cilia. So the cilia is gone. Not only will it burn off the cilia, but it will actually cause that columnar to squish down to a squamish cell. So now you have a smaller epithelium without any cilia protecting it. Which leads us to the most common symptom that smokers have, which is what? Cough. They are always coughing. They have a smoker's cough. Why? Because the epithelium in the airway is vulnerable. They have no cilia, nothing to protect it, and it's a constant irritation, constant. Okay. The good thing about this is that when they stop smoking, it can regenerate back to the normal epithelium. Okay, so that's a good thing. Which brings us to another kind of finding. When patients stops, or I should say smokers stop smoking, they still have a cough, but what's different about the cough now? If you've ever seen anyone that stopped smoking. It's very productive, okay, especially like in the beginning phases when they quit smoking. Very productive. They're coughing up all types of mucus and everything. Okay, so they're coughing up all the gook that's been sitting there for how long? Okay, because now they have the cilia that's back that can sweep it out. So that's that particular adaptation. Now on your picture, I know it's not a great looking picture of metaplasia, but in the corner there you have what are called squamous cells. So those are the squamous cells in the corner. And in the midline, those cells that's kind of lined up in the row, those are actually cuboidal. Okay, so this kind of showing you from one transition to the next. So, one more thing I want to add to this. Critical thinking question for you. If you have an individual that's able to convert one cell type to another in the same tissue, do you think that that's dangerous? Yes. Understand that if this individual now can change the genetic makeup in their body to change one cell type to another in the same tissue where that's not supposed to happen, that can be a little dangerous if you think about it. Now, we do not want to say by no means this is precancerous at this stage. However, for the simple fact that they're able to have that sort of adaptation and changeover, is it a possibility that it may be a little easier for the body to lead down the road to a dysplasia? Yes. This is why, one of the reasons why studies have shown with cigarette smoking, because they know this adaptation occurs, that it's a little easier for them to lead into, cancer, just because of that. And then on the flip side, the carcinogens, that's a whole other story we'll get into later. But just keep in mind that that's not such a good thing. And we'll see this also later on, even in the GI tract. So the same thing goes on when people have GERD,